Example 2, the radioactive element americium is used in household smoke detectors. It has a half-life of approximately 432 years. The average smoke detector contains 200 micrograms of americium-241. The graph is drawn for us here. So we see the starting amount is 200 and it decreases down. What is a transformed exponential function that models the graph showing the radioactive decay of 200 micrograms? What we're looking for here is the equation of the graph. So we've got our variables a and t. So we're finding a of t equation. We know the base number because its half-life is going to be 1/2. So there's going to be a vertical stretch. I'm just going to leave some space there for that. My starting amount is always going to be the vertical stretch. Normally we have a y-intercept of 1. So this means 1 must have been multiplied by 200. So this is going to be your starting amount. And that's going to be a link to the A value. So we're going to have 200 out front. Okay, my variable t is going to be here, but that's going to be linked to the time. 432 years is going to mean that it was by a factor of, this is for the b value, 432. So this is going to be linked to the b value. So this is 1 over 432 is the b value then. So t over 432. So your a value is 200, just to be clear. Your b value is 1 over 432, which, so when you multiply it by t, you get that. Part B, identify how each of the parameters are what is the a and b value. So these are the parameters right here of the function relates to the transform graph. Well, for the a, you have a vertical stretch by a factor of 200. For the b value, this means that you're going to have a horizontal stretch by a factor of 432. Because remember, b is 1 over 432, so when you're describing the transformation, it's 432. So that's how it would be in the question, is actually how you would be describing the stretch for the horizontal stretch.